I show you how you can create a hidden secret lock keypad to keep all your sensitive stuff safe. Hi guys, it's Oli here. I hope you're having a great day. In today's video I'm going to show you how you can create that secret lock keypad with the use of some Hall effect sensors. These are actually magnetic sensors, as you can see it on this short video. I'm using the SS49E, which has 3 legs. One is the plus, next is the ground, and the third is an output. It works like this. When a magnet is not close to the sensor, meaning it does not get excess magnetic force on it, it outputs roughly half of the supply voltage. In this case, it's 2.5 volts. And as the the north pole of a magnet is getting closer to the sensor's face, it outputs closer to supply voltage, in this case close to 5 volts. And if the southern pole of the magnet is getting close to the face of the sensor, it outputs close to ground. So as you can see, the north pole went closer and then the output goes to 5 volts. This is how I connected up to an Arduino Nano. It's a very simple schematic, and I'm just going to check pin A5, constantly reading the value of the output. The good thing with this lock keypad is that as far as it is based on magnetism, it can be hidden behind surfaces in a way that it's not even visible. You do not have to open up the surface to hide it behind it. It just has to be some non-magnetic material, and it shouldn't be too thick. But I show you everything how it goes. So here I connected up to the Arduino, and this is a very simple code, very similar than what I used with the photo resistor video. So as you can see, the value is around 520, which is roughly the middle ground between 0 and 1024. And as I'm getting closer with the magnet, the values start to increase. So that tells me that I'm actually pushing the northern pole of the magnet towards the sensor. Now I turned it around, so the value goes down. It is basically a very simple device. This is what is used also in ABS systems in cars. This is how they can see that the axle is rotating or if it's blocked. So I'm going to use this material to demonstrate. This is an alu debond material. You can check it out what it is. It's actually 2 layers of aluminium and it sandwiches in a layer of plastic. It's a very strong composite material, and as you can see, as far as aluminium is not magnetic material, the magnetic force lines has no problem to cross it through, so the sensor can absolutely sense that on the other side there is a magnet. This is a 3 mm or 1/8 of an inch thick alu debond plate. It's super strong, so I'm just going to mark up 4 places on it, which are going to be the 4 imaginary buttons behind this surface, and that's the magnet I'm going to use. Here are the 4 sensors and an RGB LED to show me if it's logged or unlogged. You can post this here, but it's a very simple schematic. This is what I'm going to use in today's project. During the build, I didn't want to just solder on the surface of that nice composite material, so I made a template out of paper, and I'm just fixing all the sensors on it while I'm doing all the soldering. Now, these materials could be any kind of non-ferrous metal, aluminium, copper, brass, other stuff, lead even, and wood, ceramics, glass, plastics, all different kind of material. This is really good, and per my measurements, up to 10 millimeters, so like 1 centimeter, which would be what, 3/4 or 3/8 of an inch, a little bit more even. You can easily use this, and of course with a stronger magnet, even thicker materials are totally fine to use. Anyway, so now it is all soldered up, absolutely based on the schematics I showed you. So I'm just going to put it on this alu debond, which I put some extra layer of insulation, even though it's painted, but just to be sure. So you see now it's on the back, and then the Arduino is connected up. Of course, now it doesn't know yet what to do or how to do it. It has to be programmed, but we're going to go through that just in a moment. But first, the functionalities. What do we want from a lock? Now I just put 4 digits in. So we want easy code change so that anyone can change it who has access to it, of course. We want a feedback so that the button is being pressed, visual or audio, whatever. We want to see an indicator to know if the system is on or off or locked or open. We want visual feedback for failed attempts. We want to have a lockout after X amount of trials so that we are logged out of the system, we have to wait. But of course, a successful login has to zero the lockout, the failed attempt counter, so that we can have again the proper number of attempts. And then we need also some kind of a timeout so that if we accidentally just push a button, even though these are not buttons, but so that the system doesn't just hang forever. Just after a certain time period, if not the 4 digits are in, it basically resets itself and waits for the numbers. So the next part is for those who want to understand the workings of this software here. Here are all the variables. I mean, it's going to be a little bit long, so feel free to skip ahead if you want. So here are all the variables we are using in this program. I'm going to explain them all. Arm status is pretty simple. Is the variable telling us if the system is on or off, or is if it's logged or unlocked. Mode, this is a very important one. It starts with mode 0. This is basically signifying the steps which are being followed in the software. I'm just going to show you fast. So it starts with mode 0. This is an idle state. It is actually here. This is all what the program does during mode 0. It does it over and over again, basically looking for a first button press as an input to get the key to open or close the system. Does some other things also, but basically what it does. And then when that is done, when a button is pressed, then it goes to mode 1. So this is where it is being incremented. And then it does the next section, doing the same thing, waiting for the next button press and evaluating some other stuff, and goes to mode 3, and so on and so on and so on. Next step, and when all the digits are put in, then it becomes in mode 4, when it is actually evaluating if our code key given in was correct or incorrect, and does accordingly. So that's where it follows basically the flow of operation. These 4 are the actual set key to unlock the system. I set it to 2124 because why not? You can set it to whatever you want. It can be from 1 to 4 in every digit because we have 4 sensors right now. These variables are just going to contain the information which was given with every button press. Number 1, number 2, number 3, number 4. All right. This is a variable, buttons, which is going to be telling us how many buttons, so to say, were pressed. These are not buttons, right? How many buttons were pressed in the same time for a specific digit in the key. This is important so that if multiple sensors are being registering a signal, meaning let's say someone comes with a huge magnet and puts it on the pad to just mess with the system, then it is recording that there was not only one, so to say, button was pressed in the same time. Timeout. This is the set amount of time in milliseconds. So we are talking actually 6 seconds, which I just set. It can be anything. How much time I have to put in the 4 digits after the first button press. If I accidentally press a button, let's say, I know these are sensors, but whatever, and in 6 seconds the full 4 digits are not being put in, then it's going to be a timeout event. It is going to cancel the input and goes back to original state, basically. This is the actual set time. It's a future time moment when this timeout event should happen. It's always, in this case, it's 6 seconds from present time, from the first button press. False flag. This is one of the most important variables. This is actually going to tell if our input of the code was correct or incorrect. If this stays 0, then each step of the process was correct, meaning the proper key has been input by the user. At any mistake at any digit or any double press or multiple button presses, this is going to be set to 1, and that is basically a failed attempt already. The next one is a debounce. Basically, it is just that if I put the magnet on one sensor, the microcontroller is so fast that before I would have time to remove that magnet from the sensor, it would already register it as a next digit and next digit and next digit. So we have to artificially slow down the microcontroller so that the human has time to remove the magnet from the sensor so that it's really being registered as one digit. And I set it to half a second. It can be longer, shorter. Well, maybe it's not too smart to have it shorter, but whatever. And it also, of course, determines the fastest possible time to put in the 4 digits, because it will wait half a second after every digit. Number of tries, this is the number of failed attempts in a row. Pretty simple, set to 0 as start. Maximum tries, this is how many maximum failed attempts we can have in a row before implementing a forced delay, which I set to 1 minute, basically 60 seconds. It can be strictened, like I could say after 3 tries, I have to wait a full day, maybe, whatever. You can set it whatever you want. Anyway, setup. Setting this onboard LED pin for visual feedback for a valid button press and for failed attempts and timeout events. And these two are set for the 2 different states, armed or disarmed, or on or off, or locked or open, depending on how you want it. And of course, these will be the pins, can be used to manipulate a lock, an alarm, an actuator, a servo, or whatever you want. These pins are the inputs connected to the 4 sensors, because we have 4 HAL sensors this time. Okay, so here is the core part of the software, of the program. We start with mode 0. No matter what, it pops to mode 0, idle state. It sets the arm status. As a start, we have the arm status on 0, meaning the system is open and the green lamp is going to be on, the green LED. And then here is what I told you as the idle state. So what it does is actually looking for a button press. It looks if the analog read on pin 1, 2, 3 or 4, depending on which button we are talking about, goes under 480. It's, as you remember, it was around 520 when there was no magnet around. I just chose 480. It can be set more sensitive, like 500, whatever. You can try. 480 worked fine. So when it is being registered as a magnet close to the sensor, then it turns this onboard LED on, waits a little bit and turns it off, meaning it's going to be a short blink. It changes to mode 1, and it sets the number 1 as 1. If it was 1, then it sets to 1, and increments the buttons with 1. So it was 0, so it becomes 1 now. And then immediately checks for the next one, because maybe there was nothing here, right? So it checks the second one and does the same thing, but if the second one was, then the only difference is that the number becomes 2 and buttons become 1 because it was 0 if there was no button press here. But if there was multiple button presses, then at this point the buttons is already 2. Why this is important, I will explain. So we will go through all the 4 sensors, and if any of it has been pressed, or multiple, doesn't matter. If any has been pressed, we are already going to mode 1, meaning this part is being executed, because it says if mode is equal to 1, then do this part. Otherwise, this is not being done, right? Just when it is any of the buttons pressed. So it checks. If the number 1 is not equal, this is the logic not equal to key digit 1, meaning we didn't press the right button, or multiple buttons were pressed because the buttons is more than 1, then it is a false flag, meaning it is registered as a false failed attempt. Why this is important is because if that digit 1 per our decision, let's say it would be 4 here, and I would press all the buttons in the same time. It would go here, set it to 1, but then set it to 2, then set it to 3, and at the end it would set it to 4 anyways. So if it would be 4 and I would press all the buttons, the digit, the number would be correct. But the number of buttons pressed is going to be more than 1. So because of that, it will already fail. That's why this is important. Anyways, so after any valid button press, it will implement this delay for me to be able to remove my finger or my magnet from the sensor. It sets back the buttons to 0 because for the next part I will have to see also how many buttons were pressed, and just to be sure it sets back the number 1 to 0 so that it is not being stored the value which we put in. And then here it sets the timeout moment. Here it sets a moment in the future, which is 6 seconds in my case from present time. Millis is actually a counter which goes in the microcontroller from startup and increments every millisecond 1. It's a quite big number. It increments 1000 in every second. But it's kind of the microcontroller's own time. So its own present time plus what I decide as a timeout delay, 6 seconds in this time. That's going to be the future moment. If we surpass that, if we pass that point, it is being considered as a timeout. Anyway, so mode 1, we got to mode 1. It's the same thing as looking for the button press and evaluating if either the number is correct or not correct, or too many buttons were pressed, it becomes a false flag. If it was already set here as a false flag, it just stays 1, but if it was correct in the first digit, here it will be set, if we are incorrect. And the delay again. The only difference here is that we're starting to look for the timeout, meaning if this future moment in time, which we set here, 6 seconds from that specific time, has already been passed by present, because present is already bigger than that time was, then it's a timeout. So then it triggers the timeout event. It sets all the numbers back to 0, no matter which state we are at. It sets mode to 0, meaning idle state. And it gives a blink on the LED 5 times. This, I could write basically this line 5 times, but this for loop, it repeats itself, whatever is in this curly brackets 5 times. And that's all what it happens. Then it does 5 blinks, sets the numbers to 0, mode 0, and pops out from this part, and we're back to the beginning of the software, back to the top here. Anyways, but if we manage if the timeout event haven't happened, then we got to mode 2 here. Sorry, I'm going back and forth a little bit. Then we got to mode 2. Mode 2 is doing the exact same thing, checking for button press, check if we failed, sets them back and checks for timeout. And then we go to mode 3, does the very same thing. This is the last digit which we require. And then our false flag is maybe still 0 because we are all fine. We managed everything successfully, or it's already been failed. We don't know. Of course, the false flag event, when it's a failed attempt, is not being told to the user. We just let the user to type in all the rest of the digits because that keeps it difficult to figure out the key. Anyway, so then we check for the last one, and then we get to mode 4, and mode 4 is where we evaluate how we did. This is being done only when we are in mode 4, right? So we check for the false flag. If the false flag is 1, meaning we had a failure at any point in this process above, then we are going to do the 5 blinks just to show that it was a failed attempt, and we increase the number of tries with 1, meaning it was 0, now it becomes 1. And then if the number of tries gets equal to the maximum amount of tries which we allowed, which is 5 in this case, then this part of the code is being executed. Right now it will be not, because we were on 0 as number of tries and it became just 1. So we are not being forced to wait. We have another chance to try. But if we reach the 5 tries, then the LED is going to get high, like it's going to be lit. And here is the forced delay part, which I set to 60 seconds, but this could be any any delay you want, and then after that the LED will turn off. During this time nothing can be done, like it doesn't matter what I want, nothing can be done. And after that, the forced delay, the number of tries goes back to 0. Of course, now we have again 5 tries to try to put in the proper code. If you want, here you can set the number of tries to 2. That meaning after a forced delay, the number of tries starts from 2 and increments to 5. So after a forced delay, you have only 3 more tries left. It can be done, but I just left it on 5. Anyways, this is when we failed. If we did everything correct, this is the line for that. The false flag stayed 0, so it is 0. Then we do this. The arm status is going to be not arm status, meaning if it was on, now it is going to be not on. If it was off, now it is going to be not off, meaning on. So it basically just flips the status from locked and unlocked. And of course, it puts back the number of tries to 0, because it can be that we have failed 2 or 3 times, so the number of tries is already at 2, 3. But now we put it in correct, so now we have again a clean slate, and then we can have again 5 tries. And regardless of if it was false or true, regardless if we failed or we managed, this is anyway going to set the false flag to 0, meaning we have a new chance to try to put in a new code. And that is all basically. Okay, so back to the actual application. Here is the test. This is the final trial of the product. So here is the hollow bond, as you could see on the back of the sensors. This is the magnet I'm using. So now I have those circles there as an aid for me to know where the actual sensors are. I'm going to put in the code which I set, 2124, and then the system is locked. It started from an unlocked position. So now I'm just going to feed in some totally garbage keys or codes. It doesn't matter. Now this was 2134. Of course, none of them is the correct one. So as you can see, the blinking LED on the left on the board is representing a failed attempt. I think this was number 4. Maybe this is number 5. Yes, and now we are in a lockout. So this is for 1 minute. Nothing can be done. It's just, but after 1 minute, now I have again 5 attempts. This can be all adjusted as I showed in the code explanation part. So now I'm going to put in the correct code, and it opened again, as you can see. Now the point with this is that this system can be really easily mounted on anything already existing. You do not need to have a new keypad. And look at this. Now it is completely invisible if I do not know where the sensors are. And imagine if this is mounted on a whole or like on a door or on a bigger box, or just in a secret place in your car to turn it into an immobilizer, or whatever. Like, the uses are endless. If I don't know where the sensor is, I have practically no chance to open this lock, even if I would know the combination. First and foremost, I wouldn't even know that there is a lock there. That's why it is quite cool, I think. You can use it for any project you want. And as you can see, with the right combination, it just works absolutely fine. And when you start to experience a little bit where the things are, it is not even hard to find them. It works just great. And as I said, up to 1 centimeter, or even with a stronger magnet, maybe even thicker material. In that case, it could be beneficial to put the sensors a little bit more far away from each other to avoid multiple readings. Anyway, so that is all for this project now. Guys, if you have anything to say or if you have any questions, please leave it in the comment section. Watch my other videos if you're interested in these kind of subjects. And please don't forget to subscribe. It really helps out a lot. Thanks for watching. Bye guys.